Let's see where we're at with this problem. Now that we've seen, we've got a little formula here that tells us the strength of the electric field, each little contribution, dE, that came from each one of the little dQs. All right, so let's see if we can do a little bit more with this formula. Now, traditionally, when we talk about density, we've been using rho, but that's usually associated with mass over volume. When we talk about linear density, we usually use the letter lambda. All right, now this is the charge density. It's the density associated with the charge per the amount of length. Well, it seems appropriate here. We start talking about a long, thin rod like that. Isn't it like a line? It's like a guitar string or something. So we usually replace that with lambda instead of using rho for the density. All right, now, if we look here in this particular formula right here, I'm going to clean this up a little bit and say dE is equal to, and replace dQ. Well, the reason why that's an improvement for us, we know the density, and our dx is associated with the lengths that we have in the denominator, so now we can clean up both of those. So instead of writing dq, I'm going to write lambda dx up at the top of the numerator. So I've got lambda dx in the top, and then I've got r plus x squared in the bottom. Now, further improvement on this would be dE is equal to, I'll just write it in the form of this. I like doing this when we're going to do some type of integration. And if we look here, we've got lambda, and instead of having 2 here, can I rewrite this as r plus x to the negative 2, and then dx? So we've got it kind of in a nice little form here at this point in time. And we move that lambda down so we get a better look at it. That belongs in the numerator. And it looks like so. Now this is a fairly easy integration. So if we add up, we don't really want all the dE's. Don't we want to sum up all the individual electric field contributions? And then over on this side, we've got to integrate as well. So the sum of all the dE's obviously is going to be the total electric field. Looking for some constants, we've got 4 pi epsilon naught times lambda, so I'll clean that up, put that over here, like so, looking good. And then that leaves us with this nice little r plus x to the negative 2 dx. So if we integrate that, let's have a look at that. Now, if I look, it's a fairly easy integration problem for people that are taking Calc 1 or Calc 2. I figure you're probably familiar with it. The thoughts about it are this. You probably just do this in your head. If I do a u substitution, I can say r plus x. If I want du dx, if I want to figure out what this is related to in terms of x, the derivative of u with respect to dx is actually just going to be 1. So now I don't really need to make any manipulations or anything of the integration itself because it's nice little form. It's a 1 for 1. I can just use the power rule and then get my answer here. So the negative 2, when I add 1 to it, it's going to become negative 1. And then the negative 1, of course, goes in the bottom. So let's rewrite that over here. So we end up with E is equal to lambda 4 pi EO. Okay, that's our portion here. And then the answer to the integral is going to end up being r plus x to the negative 1 divided by negative 1. And our boundaries for this particular problem are going to end up being, I'm starting at 0 on this end of the bar, and I'm going to some length. In this case, I'm actually going to a length of infinity because the bar is infinitely long. So here we are in this particular position. Now, if we start to rewrite this and evaluate it, so we have lambda 4 pi EO, r plus x to the negative 1. That goes back down in the denominator where it belongs, and it kind of looks like that. Minus 1, I'll just put the minus sign on the outside. It looks like that. All right, and we're going to evaluate this from 0 to infinity for the length of the bar. So E is going to be equal to lambda 4 pi EO 1 plus, 1 divided by r plus infinity, yes, minus 1 over r plus nothing. Okay, so we end up with this. All right, now, obviously speaking here, I'm sure this happens in calc all the time. If we have an infinitely large denominator, isn't this term going to actually approach 0. So we can basically negate that because this is going to be an extremely small number, infinitely small. So let's just call it 0. So we end up with this, and we end up basically with 1 over r. So let's clean it all up. So we end up with the electric field strength is going to be equal to lambda 4 pi EO.
Excuse me, please, Mrs. Linda Hammond, please dial
Got
0.
my minus sign there. Minus and a minus end up being a positive, and then we just have to multiply by 1 over r, or we'll just put the r here. All right, we're done. We now have a formula for the electric field strength for an infinitely long, thin rod using calc and summing everything up. Now, let's take a look and see what we did. We took the bar and broke it down into infinitely small pieces with infinitely small charges. Once we've got the base formula and adapted it over into finding very, very small portions, dq's, and finding the resulting de's, using density here to convert charges, which are hard to measure, into density and lengths, which are much easier to manipulate. Got the base formula here, and then used some basic calculus to come up with the final formula here. E is equal to lambda 4 pi epsilon naught times r. Voila, there we go.
Mr. Cordella, please dial 0.